Hey, my name is Tage Burnett, and this is my 595R project on using pins to solve inverse problems in heat transfer. In traditional engineering classes, we frequently take the material properties that we know, we plug them into models, and predict the behavior of systems. This is called a forward problem. An inverse problem is where you instead see the behavior of a system or measure it, and then try to determine what were the properties of the materials involved that created that behavior. This problem is actually very non-trivial and typically much harder to solve than the forward problem. A lot of research is done into methods to solve inverse problems, particularly in heat transfer where we care about material properties such as thermal diffusivity or thermal conductivity. These properties cannot be measured directly, so we typically come up with actually a forward model for these and then try to basically curve fit these models to our data by modifying the parameters in the model, such as thermal diffusivity. In this particular case, I will be focusing on thermal diffusivity, which is something I have done in the past for my research. So the setup to actually doing this, we need some data. So typically, thermal diffusivity is measured using a method called the flash method. This is where you take a disk of material, you shine a laser on the top surface, the laser is absorbed by the material, which turns into heat, and this heat diffuses through the sample. If the heat diffuses through the sample quickly, the material has a high thermal diffusivity, and if it diffuses slowly, it has a low thermal diffusivity. So usually we can measure the diffusion through the sample by taking temperature measurements either at the top surface or bottom surface of the material, and then fitting our model to that. So here we can see in the top right, I have an image of such a sample. You can see that in the middle, it is heated the most, where the laser is the most concentrated, and the temperature decreases as you go outwards radially. You can see that as well in this surface that I've shown of the same thing here on the bottom right. You can see that at a radius of 0, we have the peak temperature, and as you go out radially, the temperature decreases, and then as you increase in time, which is our y-axis, you can see that the temperature becomes more uniform. Additionally, I have an image of the power profile of the laser just to show how quick it is. The laser peaks at 1/4 of a millisecond and by 1.5 milliseconds is basically off. So in order to actually produce data, I ran some simulations with the finite element code where I used the laser as a volumetric heat source, which is modeled as being absorbed in the sample. So here you can see the heat diffusion equation that is actually being modeled in the finite element code, and this is the same equation that I want to use for my residual of the physics losses in order to actually fit my PINN to this model. So all I had to do was I had to take this equation, I had to subtract over the time term, and then you have your residual. You want this to be equal to 0. So my loss function ends up being the temperature for the data minus the predicted temperature, which I've denoted as T with a little hat, squared, plus a physics weight times the residual squared, plus a boundary condition weight times the difference between the boundary condition of the boundary condition of the PINN and also the boundary condition that we expect to have. So for example, I modeled all of the boundaries as being adiabatic, except the top surface where we have a convective boundary condition. So in order to actually go about solving this problem, I created a PINN. This PINN takes in 3 inputs. It takes in the radius, the depth, which is our z-coordinate, and the time, and it outputs the temperature. So this PINN has 3 inputs, so it's a 3D PINN, which actually means we need a lot of collocation points to really fully capture this 3-dimensional space. It had multiple hidden layers, 7 of them to be exact, with sizes shown below. I used a tan H activation function because it's differentiable, has a second derivative. And then I also ended up needing to use 200,000 data points, which I split into 100 batches, so each of 2,000 points, in order to actually model this properly. So I had several difficulties when I initially tried to solve this problem. I had actually simulated 4 different materials: silicon, copper, silicon carbide, and glass, and thought I was going to have time to fit all of them. It turned out to be much more work to get this working for even one material than I expected, so I ended up only doing silicon. Some of the reasons that I had difficulties, let's start with the image on the right. So here you can see basically the whole thing is just one solid color. So what this is showing here, this is showing non-dimensional temperature. I actually ended up non-dimensionalizing my heat diffusion equation, non-dimensionalizing my temperature and my inputs in order to solve this problem. Because the scales of time and the scales of space were all very, very different. And the model was not training well. The optimizer was having a really hard time with that. So I non-dimensionalized everything. So here on the plot on the right, we have theta, which is our non-dimensionalized temperature. Basically corresponds to the temperature rise of the sample divided by the maximum temperature. So here you can see the temperature rise basically sits at just 1 the entire time. and that's because I non-dimensionalized using the steady state temperature. There's a tiny bit of stuff happening right toward the left side of that figure, and clearly that's the part we actually care about. So when I first tried fitting my model to this, I used all of the data from the simulation, which I ran for 4 seconds, as you can see on the x-axis there for time, and obviously that did not work. The model basically just tried to predict that the temperature, or that the theta value would always be 1, because I had too much data. So that was a problem. Another problem that I had was, as you can see, the laser pulse, like I talked about earlier, basically is completely shut off after 1.5 milliseconds. So I needed to have a ton of collocation points in the first 1.5 milliseconds to get that to work as well. Once I figured out some of these things, I was able to actually make some progress. So as I mentioned, I needed to make a ton of collocation points in the first millisecond of my simulation. I needed to cut off my data, so I was only looking at the first 0.05 seconds of the simulation. As you can see here, when I go out to 0.04, there's way more stuff to be seen, and you actually capture what's happening, what we care about. Additionally, I had to non-dimensionalize the temperature in order to get my optimizer actually working. So I took temperature with radius, z, and time to theta, which has rho, zeta, and tau, which are all non-dimensionalized, so that they fall between 0 and 1. Doing that helped my model a ton. Reducing the amount of data I was using also helped my model a lot. And then, as I said, I needed to have a ton of collocation points toward the beginning of the time period. And I also needed a ton of collocation points at the top of the sample, because that's where the laser is actually being absorbed, and your volumetric heat source is strongest there and is basically non-existent in the bulk of the sample. So for that reason, I actually ended up using my data points that I had, which were from the top surface of the material. I used the locations of those, both in space and time, as collocation points, and I added about double that as well for interior points. This was really helpful because I had a ton of data points on the top surface, which I needed to really capture the volumetric heat source, and a lot of these data points also fell in the first millisecond of time. So once I sorted out a lot of the bugs from my previous model, I was able to actually get some results. So here you can see that in the end, I was able to get the model to find a thermal diffusivity of 2.8 times 10 to the negative fifth meters squared per second. The true thermal diffusivity was about triple that of 8.92 times 10 to the negative fifth meters squared per second. But honestly, I'm really happy with that. That performs roughly as well as a lot of the other models that are used for calculating thermal diffusivity, which is actually pretty cool to see. I kind of wished it would have outperformed them, but it definitely did not. And as I mentioned, I had tons of problems, so it kind of makes sense that this was the case. In order to actually get this data working, another thing I had to do was implement a learning rate scheduler. So anytime the losses started to plateau, the learning rate scheduler would decrease the learning rate, which helped significantly, and that was done with just a default module in PyTorch. And another thing that I did was I actually fit all of the data first by having a really low weight for my physics losses, 1e to the negative 12 actually. And then once I hit 50 epochs, then I slowly started increasing that by multiplying by 1.5 each epoch until the physics was modeled as well. And that was necessary because when I didn't do that, the model just got stuck at the beginning and didn't learn anything. So overall, like I mentioned, I was actually able to get a decent fit. So here you can see the predictions from the model as well as the true data. So my predicted temperatures were on the top, and the true, theta, non-dimensionalized temperatures on the bottom. You can see that they line up very well in shape. The magnitude of them is very similar, except for the maximum. The maximum for the predicted was higher. You can see that best on the surface, where we have a maximum of close to 5, where on the true data, the maximum was close to 4. So because of the way the model worked out, it didn't quite fit that perfectly, but did do well enough for the thermal diffusivity for what I wanted. So conclusions and lessons learned, I learned, first of all, you have to fit the data first and then include the physics. That was probably the most important thing I needed to do to get this to work. So tweaking the physics loss weight over time was super helpful. Additionally, I had to non-dimensionalize all of my data in order to get my optimizer to really do anything because of the various scales involved. Additionally, a learning rate scheduler is super helpful. Once you start to plateau, if you can drop that learning rate, that actually really helps you get unstuck. And so PyTorch had a great way of doing that automatically, which was super helpful. And additionally, I learned that for 3D data where I had radius, z, and time, you need a ton of collocation points in order to capture that space. So I really learned that PINNs start to break down when you have high dimensional inputs, because it's hard to really cover all of the space there. So anyway, this was my project. It turned out really well. I'm happy with it and hope you enjoyed it. Thank you.